Yuri did a chemistry major and PhD at the Department of Chemistry at Lviv State University, Ukraine. He was the faculty staff with academic appointment of assistant professor, associate professor, and vice president at the Lviv State University. He also worked as a researcher at the Max Planck Institute für Metallforschung and the Max Planck Institute für Festkörperforschung in Stuttgart. He was the head of the research group at the Max Planck Institute for Chemische Physics Försterstoffe in Dresden, Germany. Within the 2001-2023, Yuri was the scientific member of the Max Planck Society and the director of the Max Planck Institute für Chemische Physics Försterstoffe, this Department of Chemical Metal Science in Dresden. Faculty member and honorary professor in chemical metal science at the Dresden University of Technology, Germany. Since 2023, Yuri is the director emeritus at the Max Planck Institute for Chemische Physics Försterstoffe in Dresden.
Yuri got plenty of different fellowships and awards. So let me mention the fellowship of at the Institute of Physical Chemistry, University of Vienna, Austria. Alexander von Humboldt fellowship at the Max Planck Institute für Metallforschung in Stuttgart. Yuri was a guest professor at the University of Rennes, France, visiting professor at the Chinese Academy of Sciences, visiting professor at NCKN, France, adjunct professor at the University of Shanghai, China, got honorary doctorate from the National Academy of Sciences of Ukraine, Vernadsky Gold Medal of the National Academy of Sciences of Ukraine for the outstanding achievements in thermoelectric materials science, and also honorary professorship of the Institute of Low Temperature and Structural Studies of the Polish Academy of Sciences in Wrocław, where we have our national meetings for the last 60 years. And lately, Karl Hermann Medal of the German Crystallographic Society, and also award of Thermoelectric Society for outstanding achievement in this field. Yuri published incredible number of papers, more than 800 papers, and got 15 patents. Congratulations on this really excellent achievements. So, Yuri, the screen is yours, and thank you very much that you agreed to present the lecture.
Thank you very much, Mrs. and Mr. Chairman. First of all, thank you for the invitation to give this lecture here. Concerning all the achievements, I should say that, well, it's the achievements, so to say, of the people with whom I was working all these years, my co-workers. So just to make this clear, without these colleagues, it will be possible. Okay, now concerning the lecture. The lecture is a attempt to combine three different terms. One is the chemical bond, another is intermetallic compounds, and the third one is electron density. Let's start with the first one. What is intermetallic compounds? Well, the intermetallic compounds, at least we consider them on this way. They are inorganic compounds which contain elements which are left from the sinter line and around this line. What is very interesting for these compounds is the crystal chemistry. because if you look on the crystal structure, you can find coordination numbers starting with 1 and ending with 24. If you want, it can be more. So the materials show very often homogeneity range in respect of the temperature composition. What is also quite typical is that they show a lot of crystallographic disorder. Well, all of that needs to be understood in some way. And the first what you face thinking about this compound is the so-called electron deficiency. Well, you have low number of electrons in the last shell per atom. This does not allow to use the usual valence approaches to explain compositions and structures, and the chemical bonding consequently does not fit usual chemical pictures, because, well, valence-nolence, you have to think about multi-atomic bonding, and then you face problems with the many basic chemical concepts, for example, bonding polarity, which plays a big role in explanation of crystal structures and properties of inorganic materials. Though this is not something new. Already Linus Pauling in his one of these lectures mentioned that intermetallic compound still evades satisfactory solution in that of the structure and composition. What does it mean? We do not have satisfactory general theory of the composition, structure, and properties of that. In other words, we do not have a general theory of chemical bonding. Again, what is chemical bonding? Here we follow also the position of Linus Pauling, and this is very nice definition of chemical bonding because it contains two parts. The one part is to say the informational part, and the second one is psychological part, because the Linus Pauling says that chemical bond between two atoms or groups of atoms, in case that the forces acting between them are such as to lead to the formation of an aggregate with sufficient stability. This is fact. It's convenient for the chemist to consider it as independent species. Well, the definition of what we are following in the understanding of intermetallic compound. Better to say what we try to follow. Well, concept, the chemical bond is a concept in principle, and what is the concept? Then I recall the opinion of Paul Dirac, who wrote quite a lot year ago that the underlying physical laws necessary for the mathematical theory of a large part of physics and whole chemistry are thus complete known. And the difficulty is that exact application of these laws leads to an equation which much too complicated to be solvable. It therefore becomes desirable that approximate practical method of applying quantum mechanics should be developed, in which can lead to an explanation of many features of atomic system without too much computation. Well, these are some basic statements about this whole approach, what I will talk about. Which concepts we have for intermetallic compounds? We start, if we have enough electrons in the system, we can we can apply the normal valence concept, and all of the bonds are center two electron bonds, or they have lone pairs. If we reduce the number of electrons in principle, that means we move in the periodic table from right to left. We have now the Zintel-Klein model, when the electrons of the cations are used in the anionic substructure for formation of the same two center two electron bonds. And then if we reduce the number of electrons more, we have, so to say, two basic concepts. The one is the Lipps-Wade-Mingus concept, where the electrons of the cations are used in the anionic substructure for the formation of intercluster bonds and or lone pairs and intercluster bonds. Two and multi-center. This is on the one side. On the other side, we have a Hume-Rothery mechanism, which is, so to say, using all electrons available in the valence electrons. It's based on the interaction between Fermi-Seymour surface and beryllium and so on. Well, but these are two, the intermetallic compounds are somewhere in between, because they they have less electrons which are necessary for these Lipps-Wade constructions, but on the other hand, well, they do not have, so to say, from the structural point of view, it's difficult to apply in any case Hume-Rothery mechanism. Okay, so that means we need another conceptual approach which fits somewhere in between. There are many ways, of course, to think about that. The one way is suggested by Hohenberg-Kohn theorems, which says that the total energy is a unique function of electron density, and the ground state density uniquely determines the potential and thus all properties of the system. Well, if the ground state density describes the physical property of the system, it makes sense to describe chemical bond unit using also electron density in order to have the direct link between the properties and the bonding. So what can we learn if we analyze electron density? The first part, what we learn, we can, so to say, we can give a definition what is atom. Well, and what is the atom volume? Let me start here with this diagram. This average volume of the atoms in the system yttrium gallium. There are several compounds, and normally you see it that the average volume is, so to say, it's located below the straight line between the elements. Well, the general argument what you can find in the handbooks is that this is because the atoms are interacting. Well, that's all. So, and in more general, one can express this in the form of Weger's law. Okay, what can we learn more if we look on the electron density in these materials? And here we apply the Richard Vedder theory of atoms and molecules, and we use zero flux points in the volume of electron density, and the atoms are defined. The borders between the atoms are defined by these points. And what you can have, first of all, you can have here a shape of your atom, and you have the volume of your atom. So looking how this looks like in the, for example, in magnesium diboride, you see that these atoms are not so spherical like we used to draw them in the crystal chemistry. But the advantage of this is that these atoms are filling completely the space of the crystal structure. That means if we consider this atom, we have, so to say, we have a more complete description of the system. What do we learn? What do we have from this is we can learn the volume and the shapes. And then if you look on this volume of the atoms, you see it, they are not really, they do not follow this straight linear dependence. It means the volume of the atom in a system depends on the composition, but also without one composition, like here, you can have a very different volumes. And that means that this reason here is, in fact, is connected definitely with interaction, but it's very fine. It's a very fine difference also within one structure. And by the way, this allows us to enhance the Vegar's rule if we assume that the volume of atom is not constant within the binary system. It changes, then we can obtain this kind of curves. Concerning the shape of the atoms in the same system, you see they are very, very different. And again, they are not really spheres. But if you calculate now, if you have now the volume, you can integrate the charge within this volume, and then you will have population. If you integrate the electron density within this shape, you obtain the population of this shape, and then if you extract the atomic number, then you will have effective charges of this atom within the given structure. And now if you look on the charges in the same system, you see that they follow more or less our expectation, because you would expect that gallium is here electromolar electronegative. You should have negative charges, but they are changed. The effective charges change with the composition, but they never achieve, so to say, this ideal values we would expect for yttrium, something +3, no, and the same as not -3 by gallium, but they follow the same trend. Okay, what we need next, we need to visualize the bond. In order, now we have now actors, now we can visualize the bonding. And here, before we start that, let me attract your attention to this figure. These are two Q-time atoms. The blue one is barium, red one is palladium in this crystal structure. What is interesting for that is this common surface of the both atoms, this so-called patch, a barium-palladium patch. And this can be used, for example, to define coordination numbers of the atoms, because if these patches are described by solid angles, and if you calculate all these solid angles and normalize it appropriately, the whole technology is written here in this paper. But what is very interesting, you will have a sequence, so to say, of the importance of this, the size of these patches, and then you can define, so to say, the region where the patches, so to say, lead to coordination reciprocity. And this is for the intermetallic compounds are quite important, because if you apply the normal techniques like a Brunner-Schwarzenbach, then you have often the situation that if atom A has the atom B in coordination polyether, but it does not say that atom B will have the atom A, which from the chemical point of view, it's quite difficult to swallow. Well, for the titan, nickel, silicon, you see it. We can define here three different subcoordination for each atom, and you see it. The total coordination. This connects all the contacts what this atom has. It, by the way, much more as you can observe from Brunner-Schwarzenbach technology. Well, but then you see it that the coordination numbers which are highest, so to say, importance, they give you more or less the most important part of the crystal structure from the point of view of electron density. And that means we have a way more or less to come from the coordination to the bonding. But this is not enough. We need some more quantum mechanics for that. And for the visualization of bonding, you need a function which describes the behavior of electron pairs. And there are several functions of this kind which are known. We are using this electron localizability indicator. This is a product of electron density with so-called pair density distribution function. And if you compare this green one, this is LE, and compare it with the electron density, what is very interesting, this new function has much more interesting landscape as a density, because you have maxima within the atomic shells, then you have maxima between the atoms, and the appearance of such maxima is a medial indication of the bonding that you can describe, so to say, one-dimensional. On the right side is a two-dimensional case, and this you can immediately indicate the bonding and visualize the bonding. Here, for example, is a germanium-2 molecule, and here is a hypothetical molecule of the scandium with germanium. And you see it, the inner shell of the atoms are still spherical, but the outer shells, they are restructurized, and this restructuring is the visualization and characterization of the bonding. But what you can do here also, you can apply the same mathematical procedure, and then you can integrate the electron density within these new shapes, and this gives you the populating of the bonding basins of the inner shell, and so on and so on. Well, that means if we apply this combination of electron density and electron localizability indicator, we have a complete set of the categories which allows us to describe and quantitatively describe the chemical interaction in the system. And we can go, we see immediately how many atoms are participating in the bonding. We have the population of the bonding basins, and then we can split even the population of this bonding basin between the original atoms, and then we can calculate the polarity of the bonding. We can talk about electron localizability based oxidation number. So that means we have this set of categories. One can, of course, address the question: why do you need, so to say, to rediscover the wheel? Well, we know, or we have all definitions, but the advantage of this kind of approach is that we have all these definitions within one, are derived from one and the same electron density. That means if you discuss all these things, you do not lose information, transferring the information from different space, between different space. This is, in my opinion, advantage of this kind of thing. How it looks, for example, for magnesium diboride. In principle, you can say, okay, well, this is three bonded boron atom. It means we have three boron, the boron bonds. We should have boron bonds, and magnesium should deliver the electrons. This is, so to say, Zintal-like description. If we look on this, it did so. We have only these boron bonds, but analysis shows that the boron atoms, they deliver something like 96% of the population, and 4% of the population is delivered by magnesium. De facto, that means we have a multi-center bonding here, and we can quantize this multi-center by the according population distribution. And we can also here say, okay, we can also talk here about the polarity of the bonding, because you can compare the amount of electrons from the boron to the total amount, and then you can have here the polarity of the bonding, like it even here. And this gives us a very interesting situation. We have one picture for the complete possible bonding we start with homopolar bonding, which is not polar, and we have heteropolar bonding, and at the end of the day, we have a closed shell all ionic variant. But this is everything within one picture, only looking on electron density. Well, important is here, or this field is quite developed field, and longer time, one of the arguments was, okay, these are nice pictures, that's everything fine, but we know that the energy of the system is defined by electron density. Where is your energy? Well, the energy can be also expressed within this concept. In this sense, the energy of between two atoms, the energy equivalent is formed by from two parts. The one is, so to say, an interaction energy, which contains two parts as classic electrostatic energy, but not between the point charges, but between the charges within the Q-time atoms. Then you have exchange energy, which is equivalent to the covalent part of the energy. But what is also very interesting is that it's a small part of energy, which is called self-energy, and this is something which one can understand as the energy what the atom needs in order to be able to make bond. So this is not very old story. The first, what we wanted to know, can we predict with this kind of energy, for example, a relation between the diamond and the graphite? And it was very interesting that if we apply only this right part, only this interaction energy, we have a wrong sequence. We have a wrong sequence, the diamond will be more stable. Only addition of the self-energy makes the world again in order, and then graphite starts to be more stable. Okay. Concerning the energies, one very nice example, this is the bond energy in gallium palladium. This is a catalytic material, quite active one. Before we, so to say, have this all energy calculation, we sort the bonds within the structure according to the distance, with the idea, okay, the distance should be proportional to the energy in some way. So, and what is interesting that in the case of these materials, again, the closest distance, this one has the largest energy. But beside these strong energies here within the structure, they are also quite interesting contribution to the total energy. For example, palladium contributes positively to the total energy, but gallium contributes negatively. There are distances in the crystal structure which are a little bit more larger as that what I showed here. These distances are on the level of 3 angstrom. So, and this allows to do the following experiment. If we want to know, for example, for catalysis, important to know what is on the surface, and that means important to know what happens in the structure if we cleave it. And we call this operation as a virtual grinding. And if you cut the structure on the way that you have only the atoms which are held here by the strongest bond, you will have this kind of surface. And what is very interesting, this indeed so, this was confirmed by STM experiments. You really have these atoms on the surface. What was, so to say, assumed from quite simple way of thinking. Okay, so this is now the question is what one should keep in mind. The quantum chemical calculation, this is quantum chemical calculation. It gives you a numerical result. And from numerical result, one should be able to come to concept. And one example of this, I can show you. This is a quite fresh work made basically by Frank Wagner, who should be today here, but for family reason cannot be. Well, there is another way to interpret the electron density. And if you apply not the electron density, but apply the so-called pair density, and then you can calculate the number of electrons which are localized really in the volume. And you can calculate the number of electrons can be exchanged between the atoms. That means we have some sort of localized and bonding electrons. And analyzing this kind of things for some cluster material, Frank Wagner came to very interesting results. It seems that to understand what kind of bonding is in a cluster, it's enough to have this vertex degree, its number of connection of the vertex in the cluster, and the composition. And if you put these all numbers, they are integers, of course, and then you put it in this kind of equation, which nothing else, which says either I have electrons which are going for 2 electron bonds, or I may have electrons going to 3 center bonds. And then you can really solve this structure if you assume that this equation is equal of 8. It means we assume the 8 minus n number should be working in the 8 minus n principle should work here. Then you can have the solution of this equation with nothing else and the Stix numbers, which is quite unexpected results, because we came from the delocalization indexes. So what we finish here at the Stix numbers. What does it mean? What way it's open? In my opinion, it opened the ways to understand, for example, also the atomic groups in intermetallic compounds, only looking on their topology. And then you have a possibility to understand this as a set of 2 atomic and 3 atomic bonds. This is the way what we hope it will work, but this is very fresh. Okay, so this I already explained. What kind of application can I show you here? Quite good in time. The one is the so-called the problem of so-called excess electrons. What happens, for example, if the atoms have more electrons as they need for form, now let's say simple picture. For example, here, tin selenide, in principle, it's zero bonded selenium, and tin has more electrons as you need, and that means these 2 electrons are located on tin. This is one mechanism. Another mechanism is a gallium selenium. You see here, this is again 1 bonded gallium. It's zero bonded selenium, and the gallium has more electrons as they need. So what gallium is doing, it forms gallium bonds. It's so-called polycation formation. This is, we had quite recently, we had another compound which is called lutetium germanium. It's an iron bore structure type. It's nice trigonal prism columns. if we would have a calcium analogon, this electron-based electron compensated compound, it's a Sintel picture. So, but lutetium makes the same. But in this case, we have one excess electrons. And how to understand that, and how do we interpret that? You can calculate, for example, the electron localizability, and then we will see that beside the normal maxima between the germanium atoms, which would expect a germanium so you have a maximum of Li within the tetrahedron of lutetium atoms. This is so to say the picture. What is very interesting also, that if you look on the density of state, you hear this is a Fermi level, and you have another minimum of density of state, and this region, these are the region of these excess electrons. And now if you calculate to make this whole calculation with these excess electrons here, only with the state which are here, then we will see that the maximum of this Li is exactly within this lutetium-4 tetrahedron. What does it mean? It does mean that we have, so to say, another way to use excess electrons. That's for cation-cation bonds, but this is already a chain polycation. This is, so to say, another mechanism or additional mechanism. And the last mechanism we found recently in this compound, if you look on the density of state, it's again, you see here these excess electrons, the formation, the balance is here. And if you perform all this calculation, that we will see, you have again additional bonding in the structure. This is this region with 3 calcium and 1 lithium atom. But it's very interesting, not only these cations are participating in the bonding, but the anions, the gold, is also participating in the bonding. That means that so to say, one can understand it this way, the difference in the electronegativity does not allow, so to say, to form only polycation. So we have to think about the bonding, in this case at 8-center bonding, as a picture for that. On the other hand, you can say, well, this is something which is a real space analogon of the metallic, what is very often written as a metallic bonding. But here is not metallic bonding, this is 8 atomic bonding. It's a multi-center bond. Okay, do I have more, Mr. Chairman? Let's go for a little bit for physics.
Yes, please, you still have some time.
Good, thank you. Physical properties. Well, we were working longer time on thermoelectric materials, and one important property which you need to produce a thermoelectric material is that this material should be semiconductor or at least pseudo-semiconductor. Well, if we are talking about the semiconductors, then we are talking, normally our first picture is a silicon. What is silicon from the point of view of bonding? 2 atomic bonds, non-polar. So another group of semiconductors, they are so-called 3-5 semiconductors. This is the same picture, 2 atomic bonds, but have moderate polarity. Same, we can produce, so to say, a semiconductor. The next step is much more complex. Then you can take the elements here around the Sintel line and combine them with the earth alkaline or alkaline metals. We are talking about the Sintel phases. Here we have 2 and multi-atomic bonds. We have charge transferred from cation to anion. but we have moderate polarity within the anionic part of the structure. Well, the next step is much more interesting. For example, we have compounds which are like rubidium gold. Yeah, this we have the same two. Rather, this is ionic bonding already. We have strong charge transfer, and this picture was for us the starting point to look on the materials which are chemically similar to that. And we find very interesting material. It's a beryllium-5 platinum. Well, this is known material. Nobody was looking about this material as a possible semiconductor. But from the point of view you have here, in principle, quite complex type of bonding. You have here multi-center bonds, and you have two-center bonds, but they are all well-defined. And if you have the appropriate, so to say, electron population, this is complex bonding picture delivers you this density of state, electronic density of state, and this is a narrow gap semiconductor. Now this is a very nice results. If you start to measure for the first time, we measured the metal. But then we had a look, and then we discovered that we have beryllium inclusions in the material, which is metallic. And then only applying a special techniques, the so-called micro devices, we could show that this material really shows semiconducting behavior. Well, then I'm here already at my conclusions. Well, what I can say that in particular covalent bonding plays a key role in the chemical and structural organization of intermetallic compounds. It's so to say, it's just a the counterpart picture, because we are all not thinking about metals as a covalent bonded materials. And if we apply these quantum chemical techniques in position space, we have a way. First of all, we develop the system of categories for qualitative and quantitative description of the atomic interaction. And this allows a detailed description of the bonding in intermetallic compounds. For example, this allows to show that within one structure type, which is some kind of solid in the structural chemistry of intermetallic, then we can show that the same structure type can be realized with different bonding mechanisms. And we can also detect a very fine differences in the bonding with the isotopic compounds. Well, this approach offers also energetic estimation of the stability, and on this way probably prediction of new intermetallic compounds. And then it leads to a deeper understanding in some cases, even prediction of chemical and physical properties. The most important in this work was my partner, as Dr. Frank Wagner. I would like to thank him for the contribution and the long year cooperation and collaboration, and would like to thank you for your kind attention. Thank you very much.
Thank you, Yuri, for this excellent lecture, which is now open for questions, comments. We already have one, so please read it, Paulina.
From Enrico Poda. Very interesting talk. Do you think the same approach can be used to visualize non-covalent interactions, such as halogen bonding? For example, in classical triiodide. If I am not wrong, you mentioned that these calculations are aimed at studying the ground state. Is it possible to study the same model, bonding visualization, at the excited state?
Well, very nice question. So first of all, it can be applied on any system. In principle, also for triodide, but you have to develop additional categories in the topology of density and localization indicator. I think this is possible, and there are also enough publication on the cluster materials from the point of view of this approach. Excited state is a very nice question. Well, then we have to answer first the question: what is the electron density of excited states? Well, of course we can calculate something like a density of excited state and then analyze it, but I don't know what will be the result.
Thank you. Another question from Dongshen Wen. Thank you for interesting talk. I have two questions regarding the talk. The first is that if we base the analysis on electron density, which might change for different pseudopotentials exchange functionals, can we expect similar observation across different inputs? And a second question is, I'm wondering if that can be used to understand the change of bonding environments for solute atoms in alloy systems. For example, comparing the solutes in the crystal defects. Thank you, Dongshen.
Okay. Serious question. Thank you. The first is dependence on the calculation strategy. Let it be on the technical stuff of calculation. In principle, what we tried, so to say, to do, we tried to perform all the calculation with different potentials. Basically, the basic topology elements are normally the same. There will be a difference in some details. For example, if you try to understand the bonding in so to say the weak bonding, I expect here there will be probably the difference, but it has to be investigated. As far as I know, nobody made this kind of study. Concerning the second question, how to understand the environment of defects and all these things. Look, this is quantum chemistry. We can only work with ordered models. That means if you have the ordered models for your defect, you can investigate it also on this way. I hope I could answer in short way the question.
Thank you. My question, or addition to that, can you imagine that you can, instead of having periodic defect model, you can have some kind of a large cluster calculations, or this would not represent well?
Yeah, well, it depends how large cluster calculation represents the periodic model. Mm-hmm. So this is from my point of view. For investigation of this disorder or deviation of translational symmetry, we are using ordered models which can be periodic, but you can also use the cluster models. Mm-hmm. Then you need to simply to investigate how close is your model to your reality. But this I cannot give the total solution. In any case, it should be investigated.
Okay, so Dongshen, thanks for your answer.
Thanks. Thank you for good questions.
Are there any other on chat, Paulina?
Not at the moment.
So then I wonder, you discussed this intermetallic compounds. Are there any combination of particular, say, atoms of particular elements which are more stable than other ones? I mean, are there any configuration of electrons in atoms more advantageous, better to create stable binary compounds?
Well, in principle, yes, because they are some binary system where we do not have any compounds. But we have a binary system when you can have 10, 12 compounds. For example, rare earth metals with transition elements. This is the nightmare. That means there is something that at the moment we cannot answer what. I hope that applying this kind of approach, we can analyze further this kind of behaviors and try to understand what makes it so important.
Mm-hmm. And second question is, do you think that it is possible to somehow to get some information about superconductivity in binary or ternary compounds using this kind of approach?
To be honest, not. Because I'm skeptical in this sense, because, well, we do not have a criterion from the bonding point of view, the criterion for appearance of superconductivity. One can say, well, this is connected with some electronic instabilities, but I don't know the criteria and the way how to combine bonding with superconductivity.
Mm-hmm.
Mm-hmm. We made one attempt now. Well, I can mention here our recent publication in the Journal of American Chemical Society on uranium ditelluride. So where we could show that the appearance or disappearance of superconductivity, it's connected with some electronic instability on uranium.
Mm-hmm. Mm-hmm.
But this is definitely, I will not say this is a general solution, but it was an attempt. The paper should appear now in JACS.
Yeah, I must say that I personally very much like this atomic basins and visualization of properties of, in our case, minerals mostly, using atomic basins, because I think that the polyhedral representation is very much misleading. And at the level of studies of electron density, it gives a wrong impression. It doesn't say anything about electron density. So maybe at the structural level it could be acceptable, but we should go beyond what Kepler introduced in at the beginning of 17th century, and I mean beyond, say, close packing, closest packing, stuff like this, and actually, atomic basins are very sensitive to interactions, and you nicely showed this in the lecture. Thank you very much.
We have another question from the chat from Julian Hen. Thank you very much for the talk. What what is the self-energy that was necessary in the example of the diamond structure for obtaining the correct energy?
Yeah, well, self-energy is some kind the atom. Well, how to understand it? In order to make bonds, the atom should become, so to say, a motivation, and this is a motivation energy. Well, if it's not the same, but remember we had this concept of orbital hybridization, and this was a hybridization energy at that time.
Mm-hmm.
And here we are talking about atoms, not orbitals. But this is, in my understanding, this is something similar.
Mm-hmm.
Everything what you presented here was based on theoretical calculations. Are you aware of any experimental determination of electron densities for the systems you are studying?
Yes, we made also by ourselves some experimental density on intermetallics. Let's say this way. In principle, what we know that you can apply all these mechanisms also on experimental densities. The result will be dependent on the fact how good is your density.
How the thermal motion goes into this picture.
Yeah, but we all say, okay, we exclude thermal motion from that, all the things. We try to clean the electron density, so to say. Well, but for example, the effective charges, the better charges from the experimental densities, what we made, they are quite close to the theoretically calculated. Well, the problem with the problem is that it is not possible on completely correct way to extract the electron localizability functions from the electron density, because we have to apply some approximation in potential energy. But there are also publications where the people try to that, and they develop something like a experimental electron localization. But how good it is, and what can we do with that? For my opinion, it has to be really investigated, because we know that extracting electron density from experiment also requires quite a lot of different approximations. And that not every time clear which effect this all approximation may have, for example, on the topology at the end.
Mm-hmm.
And a very good quality experimental data, diffraction data.
Yeah, that's anyway that. But for intermetallics, it's not so easy to so to say to increase the data, because well, you have materials which have quite a high absorption. Then it's very it's very difficult to avoid non-spherical shape of the crystals, because they simply mechanically they are so different sometimes on isotopes that it's not possible to make spheres. And all these details what we know from the evaluation of experimental density, they play a role at the end, because this defines the quality of your density what you have.
Mm-hmm.
We have another question from Lavro Savik. Thank you for interesting talk. As far as I understand, disorder in this system poses a huge problem in extracting experimental charge densities. which could be useful to have a comparison to bonding analysis from the first principle calculations. How aware are you of any experimental studies and approaches? For example, maximum entropy methods. Okay, so that's similar questions to mine about the disorder actually.
What do we do with maximum entropy method? We principle we try to influence, so to say, our diffraction intensity in some kind of assumption. Well, I would say this is some kind of ironing of electron density.
Yeah, it's a way to remove if our assumptions, okay, the errors, right? But we still have this thermal motion.
Yeah, for example, well, if this is only thermal motion is okay, but in the intermetallics, of course, there's also a lot of other things which are more or less included into thermal motion. Well, but concerning the order again, I think such kind of studies are very interesting in the sense that you have your experimental data and then you have calculation for different ordered models of the possible disorder, yeah? And then you can probably learn much more if you compare your data with these models. At least you can understand which of this model is closer to the reality or which is far.
So if there is no more questions, thank you very much, Yuri, for this excellent lecture and a very interesting discussion.